Hey folks, for this screencast, I want to talk about this second order dynamics problem that a student of mine asked me to solve over the weekend, and I couldn't solve it. And I think it's just been a while since I've worked on problems like this, so I just had to kind of like refresh my memory. So I thought I'd, write it all down on this PDF here. So I have this PDF document that basically walks through the problem, and I wanted to just walk through it with you, post it to my, this is kind of like vibrations and controls, all at the same time. And so that's kind of like where this fits in. So basically, the idea is you have the standard mass connected to a spring and a dash pot, and then it's originally connected to a wall. The mass is 1 degree of freedom, so it can move left and right. If it moves to the right, it's a positive x, and if it moves to the left, it's a negative x. You have this forcing function here that can move the mass left or right. And the reason why I was having trouble with this problem is because I wanted to find the solution where you apply a constant force and the mass moves in a critically damped motion to a value of 1. And so the initial conditions are such that the initial position of the mass is 0, the initial velocity of the mass is 0, but then the steady state values, the steady state value of the position is 1. This value here is the settling time, so that's when the value is within 2% of the final value. And then the acceleration and velocity in steady state are both 0. And so to solve this problem, you have to use just standard sophomore dynamics. And so you say that the sum of the forces is the mass times the acceleration. Acceleration in this case is the second derivative of position, so that's x double dot. So that's what the two dots above the x are. In order to get the sum of the forces, you need to look at the forces applied to the body, and the body in this case is the mass. And so you have a force pulling the mass to the right, and that's the sign convention in this case. And then when you move the mass to the right, you have a negative kx force. That's Hooke's law, right? So the constant of the spring is k, and the constant of the dash pot is c. And then you use the Coulomb equation, negative cx dot. So it's proportional to velocity there. So you add all the forces together, and you get F minus Kx minus Cx dot, and then you plug it into Newton's second law over here, and you get Mx double dot equals, and I switch the sides, so Ma comes over here to Mx double dot, and then the forces come over to the right, F minus Kx minus Cx dot. So in standard form, what you do is you move all of the x's to one side, and then I divide the entire equation by m. So in this case, I've got x double dot plus c over mx dot plus k over mx equals f over m. Now this f over m over here is the forcing function, and these are the intrinsic dynamics. So that's why I have this dashed line around this box over here. Basically say these are the intrinsic dynamics. So the forcing function is basically all on its own. That is something that is completely independent of the internal dynamics here. So this forcing function u of t, which I'm calling, that's sort of the controls nomenclature, is the forcing function divided by mass in this case, where u is that forcing function on the right. Now, remember what I was saying over here, there was a specific problem I wanted to solve where the forcing function is constant and the system settles out at 1 meter. And so if you look at this here, basically at t equals infinity, you can plug in all these values over here. And so at t equals infinity in steady state, x double dot goes to 0, x dot goes to 0. And so you plug in x infinity, which is just equal to 1. And so you get k over m equals f over m. And so basically f equals k. And so if you plug that result back into here, you basically get this equation here that says x double dot plus c over mx dot plus k over mx is km. And so it's actually kind of interesting that basically in order for the steady state value to hit 1, your forcing function has to be equal to this k over m here. Now that's not as surprising for a controls engineer because if you look at the general form of a second order equation, you can find this in a textbook anywhere, and you have that x double dot plus 2 zeta omega n x dot plus omega n x squared, omega n squared x is equal to omega n squared. And in this case, omega n is the natural frequency of the system. So if the system oscillates, it's going to oscillate at that natural frequency. And then you have a damping ratio equal to zeta. Now, in my solution here, I have a critically damped system. And a critically damped system means that there is no oscillations. And when there are no oscillations, the damping ratio is actually equal to 1. And so the equation collapses where zeta basically drops out, and you get this equation here. Now, if we start to set some values and say that, k is 100 and m is 4, and I did it on purpose because k over m becomes 25, and the square root of 25 is 5, and so The natural frequency of this case is 5 radians per second. And then if you take that equation, you basically say, c over m equals 2 omega n. And again, the reason why I got omega n squared as k over m is because I set these two equations equal to each other. And so in this case, k over m is omega n squared, and then c over m is 2 omega n. And so that you can also look this up in textbooks as well, that the natural frequency is the square root of k over m. For a pendulum, the natural frequency is square root of g over L, and in this case, k over m is a square root of k over m is the natural frequency for a spring mass damper system. And so moving along, what I did was I took the c over m equals 2 omega n, and again, that was relating the specific form of the second order system to the general form 2 omega n, noting that zeta is equal to 1. And I plugged in 5, and 5 times 2 is 10. And then in this case, c over m is 4 kilograms. 4 goes to the other side. 2 times 5 is 10. 4 times 10 is 40. And so in this case, c is 40. Now those parameters are just there basically to denote that if you have a mass that's 40 kilograms, you have a spring constant that's 100 newton meters, and then you have a dash pot constant that's 40 newton meter seconds. You'll end up getting a second order system that is x double dot plus 10x dot plus 25x equals 25. And again, that's where 2 times 5 is 10, and then 5 squared is 25. Now, the reason this problem originally came about is because I was trying to solve this problem for my instrumentation class because we were actually looking at heat transfer into a thermistor. And the heat transfer into a thermistor is a second order critical damp system. Now, you can approximate it as first order, but I wanted to approximate it as second order, and I couldn't do it. Now, I teach my control students 4 different ways to solve these types of problems. You can solve using the standard AE to the ST, where you plug in a to the ST into the equation and you solve the characteristic equation. You can also solve using Laplace transforms, and those are basically analytic equations, so you actually get a full solution. And then there's also the Python, the numerical way. Well, not necessarily Python, but the numerical way. So you can use Python, MATLAB. You can use really anything, Fortran, C, R, whatever. But in this case, at least at my university, we use Python, and you can use the control system toolbox to solve Laplace transforms. And then you can also use the OD int toolbox from SciPy to solve a ordinary differential equation. And so what I'm going to do is I'm going to do a 2-part series here. So I'm going to do, in the first video, I'm going to solve the analytic way. So I'm going to solve this way using a to the ST, and then also using Laplace transforms. And so that's going to walk through the first 3 pages. And then in the second video, just so this video isn't too long, I'm going to solve the same problem using the control system toolbox and OD int. And so if you still stay tuned for the second video, you'll see the Python version. So let's go ahead and move on. So basically, this whole setup was just looking at the dynamics. And so the dynamics just gives us the equations of motion. And so that's what these are here. These are the equations of motion. And I think I wrote that here. These are the equations of motion with variables, and then these are the equations of motion with numbers, essentially. And so if we solve using a to e to the st, what you do is you assume a solution, x of t is a e to the st. You take a first derivative, and a is a constant, so that just kind of carries over. E to the st, the derivative of e is the s pops out. And then when you take a second derivative, again, a and s are constants, and then e to the st, the derivative of that, the s just pops out, so you get as squared e to the st. So what you do is you take these 3 forms of x, and you plug it back into your equations of motion. And so what you get is as squared e to the st plus 10a, right? And that's the 10 that comes from up here, times as e to the st plus 25a e to the st equals 0. Now it equals 0 because this is the homogeneous solution. So when you're solving this method, you have 2 solutions. You have the homogeneous solution and the particular solution. So in this case, the homogeneous solution, you set that equal to 0. You'll notice there's a constant here, so you just pop out a e to the st. And anyone who's solved a differential equation like this will notice that this s squared plus 10s plus 25 is your characteristic equation. Now, you have 3 things multiplied by each other that equals 0. You have 3 different solutions. Your first solution is that a equals 0. If a equals 0, and you plug that back into a to the st, you get that x of t is 0. And unfortunately, that's not viable, because if we go back to our time series plot, x is 0 at the initial condition, but x is 1 at the steady state. So if you use a equals 0, that's not a viable solution. Your other option is that e to the st is 0. In order for e to the st equal to 0, the natural log of 0 has to equal st, and then st has to be minus infinity. Solving for s, because s is a constant and t is an independent variable, you get s is negative infinity over t. This equation is already giving me concern because there's an infinity symbol in the top. But if t equals 0, the whole system blows up and goes undefined. And then if t equals infinity in steady state, s is negative 1. So you basically have an s that's not constant, and you have a solution that doesn't necessarily make sense and also is undefined at 0. So this is not a viable solution as well. The only other option is for s squared plus 10s plus 25 to equal 0, which again I mentioned was the characteristic equation. Now I was saying before that this system is critically damped, and critically damped basically also means that the characteristic equation has a repeated root. So if you factor this, you get s plus 5 times s plus 5, s plus 5 squared. So you have two repeated roots at negative 5. Now if you look up your differential equations notes, you'll know that the general solution for a repeated root is ae to the s1t plus bt e to the s2t, where a and b are constants. And so what you'll notice is that there's this extra t here. And that's just because of the nature of homogeneous solutions. So you put those two together and you get the homogeneous solution as this equation here, which is the same thing, except you replace s with negative 5 because that's the root right there. Now to find a and b are constants, you need to use the initial conditions, but you first have to find the particular solution. Now if you remember, the forcing function is 25. If you scroll back up to the definition of the forcing function, u of t is f over m, and I said that f over m in this case is k over m in order to get the proper steady state, and k is 100 and m is 4, so 100 over 4 is 25. And again, remember that for the general solution, the forcing function is omega n squared, and since 5 is omega n, 5 squared is 25. So again, in this case, the u of t is 25. That is a constant, so you assume the particular solution is also a constant. And so x is c, that constant. The derivative of a constant is 0, and the derivative of 0 is 0. So the velocity and the acceleration are 0 for this particular solution. So if you plug in these three values into the equations of motion, x double dot is 0, plus 10x dot, that's 0, plus 25x, x is c. So those two cross out and you get 25c is 25, and so in this case c is 1. So now you can put the whole thing together, homogeneous and particular solution. So you've got the particular solution over here, and then the homogeneous solution here. The initial conditions here, we have that the initial position is 0, and the initial velocity is 0. If you plug in 0 for time for the position, the 1 will come down. E to the 5 times 0, e to the 0 is 1, so you just get a. And then you plug in 0, b times 0, that all goes to 0, so you get 1 plus a plus 0 equals 0. And so in this case, a is negative 1. So you found your first constant and you can move on. The second constant, what you have to do is you first have to take a derivative. So the derivative of 1 is 0. The derivative of ae to the negative 5t is negative 5ae to the negative 5t, again, because a is a constant, the negative 5 pops out. And then the second term, you have to use the chain rule, because unfortunately you have a t and an e to the negative 5t. So I'm going to take the derivative of the second term first, so you get negative 5b te to the negative 5t. And then you take a derivative of the first, so you get the derivative of t is just 1, so you get b times 1 e to the negative 5t, and again, that's the chain rule there. So once we have the derivative of our total solution, we plug in 0 for time, and we get negative 5 here, e to the 0, which is 1. Then negative 5b times t, well, t is 0, so that whole term goes to 0. And then plus b e to the 0, which is just b. So you get negative 5a plus b is 0, and in that case, b is 5a, and so b is negative 5. You plug negative 5 into b and negative 1 into a, and you get this solution here, 1 minus e to the negative 5t minus 5t times e to the negative 5t. So that is the way to solve that equation using ae to the st. Now, if you were to use some Laplace transforms, the derivation is, or the solution rather, not the derivation, the solution is completely different. So what I'm actually going to do is just anticipating using the Python control system toolbox. I'm actually going to replace that 25 with a lowercase u, the forcing function. And so what you have to do is you have to go to your Laplace tables, and the Laplace transform of the derivative of f is s times big F, where f is in the Laplace domain, minus the initial condition. And then the second derivative, you get s squared times f, minus s times the initial condition minus the derivative of the initial condition. And so in that case, the Laplace transform of x double dot is s squared times x, big X. So I basically go from a lowercase to a capital. And the lowercase letters are in the time domain, and the capital letters are in the Laplace domain. And then you subtract off those initial condition terms. But if you recall at the beginning, I set all the initial conditions equal to 0. And so those terms just go away. Laplace transform of the first derivative is then just 1s times x. Laplace transform of x in the time domain is big X, capital X in the Laplace domain. And so the reason why I put the lowercase u there is because I wanted to take the Laplace transform of the forcing function and get u in the Laplace domain. So if you take a Laplace transform of both sides, you basically just get s squared times capital X in the Laplace domain, plus 10, 1s pops out, times capital X, plus 25, the lowercase x becomes capital X, and then the lowercase u becomes big U. Now you can pull out an x just like we've factored out the ae to the st. The only difference is we're leaving x over there. Notice that you still get the characteristic equation, which I think is kind of interesting. Now again, what you can do is you can factor this and get 1 over s plus 5 squared, and you can also bring u to the other side, and this is a standard transfer function, output over input, and this is our transfer function. Now in order to solve this in the Laplace domain and take an inverse Laplace, we have to take into account the forcing function. So the forcing function in the time domain is just 25, which is a constant, and if you go over to your Laplace tables, the Laplace transform of a constant is a over s. And so in this case, we get 25 over s. If I plug that in, I pull u over to the other side. Instead of having output over input, I have output equals input over times the transfer function. U is 25 over s, and so I get 25 over s there. So what we need to do is we need to inverse Laplace this thing. But in order to do that, we unfortunately need to use partial fractions. If you look up your partial fraction rules, you'll find that for a system that's like this, with 3 roots, you have 3 terms. A over s, that's the first root, and then b over s plus 5, that's the second root, and then you have c over s plus 5 squared, which is basically a combination of the third root. And so now you have coefficients a, b, and c that you need to solve for. In order to solve that, what I did was I multiplied by this denominator here, s times s plus 5 squared. And so that cancels on this side, and so I just get 25 on the left. And then you'll notice that this kind of just trickles through on the right here. I'm going to kind of hand wave this part because this is just basically a bunch of algebra. S here is an independent variable, and so what you can do is you can plug in s equals 0. And if you do that, the latter 2 terms drop out, and you get a equals 1. If you plug in s equals negative 5, the first 2 terms drop out, and then you get c equals negative 5. And then finally, I plugged in s equals negative 4 because what happens is negative 4 plus 5 is 1, and that's an easy equation to solve for, and you get b equals negative 1. When you inverse Laplace, the inverse Laplace of a over s, if you go to your Laplace tables, the inverse Laplace of a over s is just a, so that just comes out to a. The inverse Laplace of b over s plus 5 is this term here, so you get b e to the negative 5t. And then finally, you look at t e to the negative at, that's 1 over s plus a squared, which is exactly what this is. So the inverse Laplace of c over s plus 5 squared is ct e to the negative 5t. Since we solved for a, b, and c, we can just plug those inverse Laplace terms in there, and we find that the solution is exactly the same as what we got when we solved it this way. So that's how you solve basically to recap, we had our second order system here. That's a spring mass damper that oscillates. And we looked at the equations of motion, Newton's second law, some of the forces on the body, put the entire thing together, found the forcing function in steady state, converted the entire system to a general second order system with a critically damped system where zeta is 1, then plugged into some numbers to give us a critically damped system, and then here is our equation of numbers. We then solved the equation using ae to the st, and we found our characteristic equation, and we found that we had a repeated root. We then plugged that into our general equation here, and then we found our particular solution, which was just 1, put the entire homogeneous solution and particular solution together, and then used our initial conditions to solve for our constants a and b, and found our final solution there. Then for the Laplace transforms, what we did was we took the Laplace transform on both sides, and we basically found that our transfer function had the exact same form with our characteristic equation here, and our 2 roots at negative 5 and negative 5. Once we plugged in our forcing function in the Laplace domain, we found our transfer function, which included the forcing function in there, 25 over s times s plus 5 squared. In order to inverse Laplace this, we did a partial fractions to get three distinct terms, and then we used the Laplace table to inverse Laplace those three terms. We then just use basic algebra and the fact that s is an independent variable, just like time. Time in the time domain, t, is an independent variable. S in the Laplace domain is also an independent variable. And so we were able to just create three equations for three unknowns and solve for a, b, and c, and then plug that into our time series solution and got the exact same thing. So that concludes this portion of the video. So I'm going to pause the video here, or basically end the video here, and then I'll go ahead and see you in the next video where we plot this time series solution, but then also solve the equation using the Python control toolbox as well as Python ODE int. So I'll see y'all in the next video.